Okay, so Kirchhoff's laws for parallel junctions. I've got a nice parallel junction here. It's actually just a parallel circuit. There's no extra junctions or anything like that on top of this one. It's just a parallel junction. Three resistors connected in parallel to one another to a common power source. So we'll put the positive side of the source there, which means that the current is going to be flowing out this way, and eventually current flowing down each independent branch. So we'll have multiple branches to this circuit. And of course the current will come back again and recombine as it comes back to the source. Okay, so we could talk about having I total at the source, and of course over here again it will have combined at the end of the circuit to be I total again, but before it branches off it'll be I total, and once all the branches recombine again it'll be I total again. So I could talk about the current going down this branch as being I1, the current going down this branch as being I2, and the current going down the third branch as being I3. Now each branch in this case is branch 1, branch 2, and branch 3. And it just so happens that I've chosen to only put one resistor per branch. Okay, I could have chosen otherwise, but for this simple explanation, one resistor per branch. Yeah?
So if you had more than one resistor on one branch, it would be series and parallel?
It would be a series junction within a parallel junction. And we're going to get to that. We're going to do junctions within junctions. Okay, so that, don't worry, that's coming. But that probably wasn't in your grade 9 course. So that'll be new. And I like these. They're kind of like puzzles. They all fit together nicely. All right, so I've got current 1, current 2, and current 3. Of course, this one, because there's only one resistor per branch, I'm going to just call it resistor 1. This one will be resistor 2. This one will be resistor 3. And again, I could connect up a multimeter, and I could measure the voltage across each of these loads, across each resistor. And therefore, for each resistor, I could have V1, V2, and V3, the electric potential difference across each resistor. Now I've jammed all those labels in there. I can also have, well, there must be a total resistance for the circuit, and there must also be, if I measure the voltage across the circuit or across the junction, there must also be a total voltage for the circuit, for the junction. Okay? So I want to start off with an analogy that we talked about once before. We talked about there being kind of like a water pump pumping water up to the top of a waterfall. Okay, and you know that for a water pump pumping water up to the top of the waterfall, you have to give potential energy across a pump to get the water up to the top of the waterfall. And then as the water gets up to the top of the waterfall, it coasts along the top, and then it might fall down 1, 2, 3 parallel waterfalls. And as the water crashes down, of course it goes back to the pump again. But what can you tell me about the changing gravitational potential energy that the water molecules experience between this fall, and this fall? How does the gravitational potential energy compare between all those 3 falls? Should be the same. And so based on that type of analogy, if we've raised up an electric potential energy for every bundle of charge that goes out of this power supply, what can you tell me about the drop in electrical potential energy across each resistor that's connected in parallel? Should be the same. And so that logic gives us this idea, that V total across an individual junction is going to be equal to V1, equal to V2, equal to V3. And we're going to stop at the third one because we've only got 3 resistors, but equal to V4, equal to V5, equal to V6 if there was that many branches to this parallel junction. Okay? So this is the voltage again across branch 1, branch 2, and branch 3 are all equal to the total voltage across the junction. Okay? Now I want to use that idea, and I'd like to also talk about the idea of current. So if I talk about this is the total current, this is current 1, this is current 2, and this is current 3, you guys tell me, how, if this is a current flow, how should current 1, 2, and 3 relate to current total? What do you think mathematically? Yeah?
Current 1 plus current 2 plus current 3 equals current total.
I like it. So you can see that they're breaking apart as they branch down these different branches. We could say that current total, according to Alex, and he's totally right, should be equal to current 1 plus current 2 plus current 3. And then, of course, coming out the other side of the junction, those currents would recombine to go back to the electrical power source, back to a current total again. Okay, so and I'm not even going to bother talking about some waterfall analogy for that. Well, I mean, I may as well. Look, hey, if I got a current of water going this way, some of the water goes this way, some of the water goes this way, and some of the water goes this way, don't you think it would be the same flow rate of water coming back this way at the bottom? The waterfall analogy still sort of holds up. I mean, I won't dwell on it too long, but it does hold up. Now, having said this, what we've said here, I'd like to remind us all that Ohm's law never disappears. V equals IR is always there. For every one of these resistors, V equals IR is always obeyed so long as they are ohmic resistors. So I could say V equals IR, that's wonderful, but I could rearrange it to get I equals V over R very simply. Just taking the R over to the other side of the equal sign, or dividing both sides by R, I'd get I equals V over R. And I'd like to sub this form of Ohm's law back into this equation to see if we can come up with a new law. Okay? So if I had V over R for I total, it would be V total over R total. You know, if I could measure the total voltage and know the ohms, V total over R total should be equal to the total current. And set that equal to V1 over R1 plus V2 over R2 plus V3 over R3. Now we're going to try a similar trick to what we tried before. This time, though, it's the voltages that are all equal, according to what we said at the beginning. Set all V's equal. Because this is a parallel junction, we can do that. The V's are all equal. We already said that. So instead of saying V2, V1, V2, and V3, V total V1, V2, and V3, I'm just going to state them all as just being V. Okay? So I could say V over R total equals V over R1, V over R2, V over R3. Now once again, I got three terms, each with a common factor. What's the common factor? V. Factor it out. So I can say V over R total, V times 1 over R total. It's the same as saying V over R total. And I could say V times 1 over R1 plus 1 over R2 plus 1 over R3 is the same as saying V over R1 plus V over R2 plus V over R3. Just factored it out. Now you can probably see that I could cancel out the V's on both sides at this point. And you get the third law, and I'm going to bring the third law and I'm going to just pop it up here because I have space. My resistance law for parallel junctions is going to be 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Alright, now mathematically this is the one that troubles grade 9s the most if you try to do the resistance of a parallel junction. So let's try it. I mean, we're not in grade 9 anymore. We should be able to handle this. I'm going to give you three resistances, R1, R2, and R3, and I want you to figure out theoretically what the resistance of this whole junction should be, that is R total, if you have these three resistances, okay? So here's your three values. R1 is going to be 107.3 ohms. R2 is going to be 50.0 ohms, and R3 is going to be 49.6 ohms. R2 is 50.0, yep. Trying to get myself a really tidy 3 sig figs. Alright, so if I actually make use of this formula here, and I sub in my values, I could say 1 over R total is going to be equal to, I could say 1 over 107.3 ohms plus 1 over 50.0 ohms plus 1 over 49.6 ohms. And here's what I want you to do. We're going to keep the left as it is. for now. And I want you in your calculators with decimals, do 1 divided by 107.3 plus 1 divided by 50 plus 1 divided by 49.6. Tell me what you get. Okay. 0.049. Can you keep on going with it?
4.8.
Is it 4.8? 0.049. 4.3, yeah. 4.5. 4.7. Beauty. All right. Now, as far as the units, where are the units? Should it be ohms or 1 over ohms? You tell me. Can you see the ohms are in the denominator each time? So we could say ohms can go on the bottom, or some people rate it as ohms to the power of -1 at this stage. But let's just leave them on the bottom. We can see it that way. What do I need to do to find the resistance? Is this the resistance? Yeah, cross multiply or invert both sides. However you want to talk about it. Do it to the exponent of -1. You know, there's lots of different ways to express this idea. Let's cross multiply it, or do it to the exponent of -1, or invert the value. 1 divided by 0.049434547 should get you a value, but what will it do to the units if I invert it? Pop them up to the top, right? So I could say that our total is equal to, well, what do you guys get? I get somewhere around 20. Does that sound good to you? Don't just say yep. I want to see the calculation. 20.28? Okay. I get 20.288 approximately. 20.288 ohms. And if I round it off to 2 sig figs, or what was it? 3 sig figs. 20.3, is that what you said in the first place, Scott? Okay, sorry. 20.3 ohms approximately. Now I want you to notice something about this resistance for this circuit, or for this junction. 20.3 ohms. Compare that numerically to all these resistances over here. Is it greater than or less than? Now we've become accustomed to resistors in series having a total resistance that's greater than any of the individual resistors. In fact, we've done it as a sum. When they're in parallel, they're less than. I want to give you an object lesson that you could take to McDonald's. Okay? Seriously. It may affect your career one day. Okay? So you take yourself some straws at McDonald's, and you can put them back afterwards. Recycle, reduce, reuse. Okay? Take yourself some straws and put 30 of them in series. Fit them together end to end. And ask a friend to blow. And ask them qualitatively, how hard is it? What do you think the answer is going to be? It's pretty hard. Turns out that straws resist you blowing, and the more you put in series, the more they resist. That's in series. Got it? Take the same 30 straws and jam them in your friend's mouth. I mean, gently place them in your friend's mouth in parallel. You know what I mean by in parallel? Like in a bundle? Stick 30 straws in their mouth in a bundle and then tell them to blow. What are they going to find? Easy. Turns out the resistors, or things that resist a flow of any type, placed in parallel, decrease the resistance relative to an individual resistor. But resistors placed in series, and you can try it with drinking straws, doesn't have to be at McDonald's, it can be at any one of those reputable restaurants. Put them in series, and you're going to find a greater resistance. Okay, a nice little game you can play to explain electricity to your buddies after school. Fun, eh?